Somewhere in northern Finland, a furnace has not been cold in decades. It sits at the heart of a copper smelter the size of a small town, and at this moment it is consuming roughly 12 tons of copper concentrate every hour, running at temperatures above 1,200 degrees Celsius. The building around it hums with instrumentation, with heat exchangers, with pipes the diameter of a car running in every direction. Outside, a different kind of plant stands attached to the smelter like a second organism, a forest of absorption towers and catalyst beds and acid coolers that the uninitiated might mistake for a petrochemical refinery. It is not. It is the reason the smelter can afford to exist at all. And the substance flowing through it was, until roughly a century ago, simply released into the sky, killing everything downwind for miles. The question is not how you smelt copper. People have been doing that for 7,000 years. The question is what happens to the gas. Every ton of copper you refine from sulfide or releases sulfur. Not a little sulfur, enormous quantities of it, driven off as sulfur dioxide in concentrations that can exceed 10% of the total off-gas volume. That is a number worth sitting with. The air you are breathing right now contains roughly 21% oxygen. Imagine replacing half of that oxygen with a gas that corrodes your lungs, kills vegetation at parts per million concentrations, and dissolves into water to form sulfuric acid. That is what early copper smelters poured into the atmosphere, day and night, continuously. The copper basin in Tennessee, smelted heavily from the 1850s onward, had stripped tens of thousands of acres of forest bare by the early 20th century. Photographs from that era look like images of a dead planet. Modern environmental law prohibits that. But here is the puzzle that drives this entire episode: capturing sulfur dioxide is extraordinarily expensive if you treat it as waste. The scrubbing equipment, the neutralization chemicals, the disposal, it would add a cost burden that would make many copper deposits simply uneconomical to process. So the engineers did not build a better waste disposal system. They built a factory inside the factory. They turned the poison into a product. And that product, sulfuric acid, now subsidizes the cost of making the copper itself. In some operations, the acid revenue covers a meaningful fraction of total smelting costs. By the end of this video, you will understand exactly how that trick works, and why it required a furnace design that most people have never heard of. Start with the ore. Most of the world's copper comes not from pure copper metal but from sulfide minerals, chalcopyrite being the most common, a compound of copper, iron, and sulfur. When you heat it, the sulfur does not stay bound to the metal. It leaves. In older reverberatory furnaces, the ore was heated in a large shallow bath, and the sulfur dioxide that evolved was relatively dilute, often below 2% concentration in the flue gas, mixed with vast quantities of air that had been used to keep the fuel burning. 2% sulfur dioxide is difficult and expensive to convert to acid. It is too dilute to process efficiently. This is where the flash smelting furnace changes everything. The technology was developed in Finland in the late 1940s, largely through the work of engineers at what became the Outokumpu company, and it represents one of those rare moments when a single process innovation reshapes an entire global industry. The principle is elegant in a way that only becomes obvious in hindsight. Instead of heating a bed of ore from below, you dry the concentrate to a fine powder and blow it downward through a burner into a reaction shaft, a vertical column roughly 10 meters tall and perhaps 3 meters in diameter in a typical installation. The particles are suspended in a stream of industrially pure oxygen rather than air. The result is combustion so intense and so oxygen-rich that the reaction is essentially instantaneous. The sulfide particles ignite in mid-fall. The copper and iron compounds melt and drop to a settling bath below. And the gas that rises out of the reaction shaft is not the thin, dilute fume of a reverberatory furnace. It is a concentrated stream where sulfur dioxide can reach 12% or higher by volume, sometimes considerably more in optimized oxygen-enriched configurations. Engineers at Finnish and Chilean and Japanese smelters operating this technology have measured off-gas concentrations consistently in the 10 to 15% range during steady operation. Now you have something you can work with. The gas stream leaves the furnace at temperatures around 1300 degrees Celsius and is first passed through a waste heat boiler, a device that captures the thermal energy to generate steam, cooling the gas to roughly 350 degrees Celsius in the process. This is not a courtesy. The downstream acid plant cannot accept gas this hot, and the heat is worth recovering as electrical power or process steam. Then the gas passes through electrostatic precipitators, which strip out the fine dust particles, copper and iron oxides carried over from the reaction. You cannot send dust into the acid plant or it will coat and destroy the catalyst beds. What remains is a cleaned, concentrated stream of sulfur dioxide and residual oxygen, moving toward the contact process acid plant. Here is where chemistry takes over from metallurgy, and the mechanism is worth understanding because it is genuinely clever. The gas enters a series of catalyst beds, typically 4 stages, packed with vanadium pentoxide catalyst supported on silica. At temperatures between roughly 400 and 600 degrees Celsius, the catalyst promotes the reaction of sulfur dioxide with oxygen to form sulfur trioxide. This reaction is exothermic, meaning it releases heat, and the beds are designed with heat exchangers between stages to keep the temperature in the optimal window. Push the temperature too high and the catalyst efficiency drops. Too low and the reaction stalls. Which of these machines would you least want to be standing next to, the flash furnace dropping burning concentrate at 1300 degrees, or the absorption tower filling with fuming sulfuric acid? Tell me in the comments. The sulfur trioxide then enters absorption towers, tall columns where it meets a controlled stream of concentrated sulfuric acid, roughly 98% pure, flowing downward over ceramic packing. Sulfur trioxide reacts with the water component of this acid to form more sulfuric acid. You cannot simply spray water at sulfur trioxide, it reacts so vigorously that it forms a fine acid mist that cannot be captured and would escape the absorber entirely. This is the detail that trips up most people who think the process sounds straightforward. The absorption into near anhydrous concentrated acid is the precise trick that makes the gas fully capturable. The product is drained from the bottom, cooled in titanium heat exchangers, and stored in tanks holding thousands of tons. Modern double-absorption contact plants operating on high-concentration smelter gas achieve conversion efficiencies above 99.5%. That figure is not incidental. It is regulatory. Sulfur dioxide emissions from the stack are measured continuously against national and international limits, and the acid plant is the primary means of meeting those limits. The engineering of the acid plant and the engineering of emissions compliance are the same engineering. Now for the false belief that almost everyone carries into this subject. The common assumption is that copper smelters capture sulfur dioxide because regulators force them to, and that the acid plant is a cost, a box to tick, a machine that runs at a loss to satisfy environmental permits. The reality, once you look at the numbers, runs in exactly the opposite direction. Sulfuric acid is one of the most widely produced industrial chemicals on Earth. It is essential to fertilizer manufacturing, to ore leaching, to steel pickling, to dozens of chemical processes. A large copper smelter producing roughly 300,000 tons of copper per year will generate roughly 1 million tons of sulfuric acid annually as a byproduct. At market prices that have ranged over recent decades from $30 to over $200 per ton depending on supply and demand, the acid stream represents revenue that can be measured in the tens of millions of dollars per year, sometimes far more. In periods of high acid prices, the acid plant does not merely offset its own cost, it actively reduces the net cost of producing the copper. The engineers are not neutralizing a waste stream. They are running 2 factories simultaneously inside one building, with the output of one paying part of the operating bill of the other. Think of it this way. The furnace is like a machine that burns expensive fuel but generates a useful exhaust. Most machines vent the exhaust. This one catches it, refines it, and sells it. The poison becomes the margin. That is the actual trick, the one you can explain to someone in a sentence. Flash smelting produces off-gas concentrated enough to run a profitable acid plant, and the acid plant turns an environmental liability into a revenue stream that helps make the copper economical in the first place. The constraint and the business model are the same object. There is something quietly extraordinary about that. An industry that spent its first century poisoning entire valleys eventually built a machine that profits from capturing the poison. Not because the engineers were idealists, but because at sufficient concentration, sulfur dioxide is not waste. It is feedstock. Every giant machine hides one piece of engineering nobody notices. Subscribe for the next one.